Number 10. Adila and Brandon both travel to work each day. Information about their past journey times in minutes is given in the table. On Monday, they each took 60 minutes to travel to work. Calculate the standardized scores for the two journey times on Monday. Before we start this question, I just want to point out that GCSEs always seem tedious and feel like they have no value to it, but this is actually a real life application. Standardized scores, for some exam boards at least, are used to calculate if you miss a paper, for example. It's used to estimate what score you would have got, and they apply that to your real grade. I thought I'd just point it out before we start. So back to the question. So we're given two people their mean time and their standard deviations for their previous journeys, and we need to calculate the standardized scores. And I say just move straight to the formula because it will help you understand what the standardized score actually is. So, the standardized score is equal to the value, subtract the mean, divided by the standard deviation. The idea is that you basically, it's a bit like standard deviation if you think about it. It's a similar measure, and the idea is you can compare the two values, or you can compare two data sets together because of this. So we need to actually calculate the standardized scores for each of the two journey times. So let's do it for Adila first. I'll double check, but I think you need to remember this formula. I don't think it's given in the formula book or anywhere else. So we need to do the value, and the value for both of them was 60. So we need to do 60 minus the mean, and the mean for Adila's was 75, and then divide it by the standard deviation, and the deviation was 10. Doing this, we type it into the calculator, and we get negative 1.5. Now we'll do the same thing here for Brandon. So Brandon, again, we take the value, which is given to be 60 again. We subtract his mean, which is 65, and divide it by his standard deviation, 4. This gives us negative 1.25. And there's our 3 marks. So as long as you just knew the formula, from there it's really straightforward. Part B. Using your answers to Part A, explain which of Adila and Brandon had the better journey time on Monday. Now for this part you need to be careful. If anyone tells you to remember, oh, a higher standardized score means X or Y, no, you need to look at it in context. Because if I was to say that the mean was for the marks instead of journey times, then surely you'd want a higher mark for your exam. But in the context of minutes and your journey time, you want your journey time to be as low as possible. So who had the journey time as low as possible? And now I can actually explain what standardized scores actually are. It basically shows your relative standing of a specific value with respect to the dataset. And Adila had a negative 1.5 and Brandon a negative 1.25. A standardized score of 0 suggests that you're basically at the mean, or the expected, you're basically at where everyone else or your previous datasets mean. And that makes sense. You'd have 0 on the numerator because the value in the mean is the same. So the idea is the lowest standardized score here in this context will be the better one because it suggests that the journey time in minutes will be the lowest for Monday. So we'll say that Adila, because she had a standardized score of negative 1.5, and therefore we'll say she had the better journey. Part C. Explain why standardized scores are appropriate to use in this context. Well, the idea is the formula basically shows the values and the mean and the standard deviations. So all three components are satisfied there. But what the main key component is that we can see that the means and the standard deviations are different. Now this tells us the distribution of the data, if we were to sketch it over a relevant diagram, would be different shapes. Now when I say the phrase, I need to hold you to a standard, that instantly should make you think about consistency. If you hold something to a standard, therefore like your chocolate bar or your favorite ice cream, you're always going to hold it to a specific standard, i.e. make it consistent. So in order to compare the values, they need to be consistent, and so standardized scores allows us to do this, and because they are basically, the clues in the name, standardized. Question 11 says that the time series graph shows information about the total amount of money in millions of pounds spent in the UK by overseas tourists for each quarter between 2011 and 2013. Divya says that the time series graph shows seasonal variation. Explain whether or not she is correct. So let's highlight the keywords we have here. Explain and seasonal variation. Now we need to actually know what these two mean. Explain it just means give a reason. So we need to say yes or no to whether it has got seasonal variation and give a reason for that. So seasonal variation. Well, what is seasonal variation? If you think about it out of context for statistics for just a minute, well, if you think about seasonal variation, let's look at it in respect to ice creams. For ice creams, you'll see that there's high demand in the summer when it's nice and hot, but in the winter, you're not going to be wanting an ice cream, at least the general public anyways. So that's seasonal variation. So what you'd expect if you saw the quantity, for example, if that was on the y-axis instead, you'd see high peaks at the quarter 2, which is the summer quarter, because quarter 3 and 4 are autumn and winter, and that basically indicates seasonal variation because you're seeing a pattern. Every summer you see high demand for ice creams compared to the other seasons. So the point is, are we seeing seasonal variation? At each of quarter 1 for 2011, 2012 and 2013, the corresponding values are plotted here, here and here. Now, if you can't divide the years up, so you can say that the new year starts at quarter 1, so just about here, and then also just about here, where you can see that this is consistently the lower value. For quarter 1 of 2011, out of all the quarters, it's the lowest value. For 2012 and 2013, the same applies. So the idea is this is a pattern, it's always the lowest value. And we can say the same for quarter 3, as we can just spot that that is the peak. And you can see that this value, this value, and this value are all for quarter 3. So it doesn't have seasonal variation. We can say yes, because it follows a regular pattern. And it's repeated at the same time every year for 2011 through to 2013. You're also welcome to use the first quarter as an example. Part B. Divya considers finding 3-point, 4-point, or 5-point moving averages for the data in the time series graph. Explain which of these moving averages is the most appropriate to find. I'm going to rephrase the question is, Divya wants to find a moving point average. What is an appropriate number? And so just answering this question, you'd instantly say 4, or I'd hope you'd say 4 anyways, because in a year you have your summer, autumn, winter and spring. You have your 4 seasons, and naturally you also have 4 quarters. So you can see that we have 4 quarters here. So it makes sense that you want to use a 4-point moving average. If you use a 3-point moving average, well, sure, you're using the quarters 1, 2 and 3, but what about number 4? So we can say that it's indeed the 4-point, and this is because of its 4 quarters. Divya wants to calculate an estimate for the spending in the UK by overseas tourists in the quarter 1 of 2014. Part C. Describe how Divya can use moving averages, the mean seasonal effect, and the time series graph to do this. And just note that it's a 5 marker. I'm going to pick out the keywords here, and here it is just calculating an estimate, and we're going to look at quarter 1 and then 2014, and the keyword here is describe. Now you might get carried away because you might have seen me answer other 5 markers using actual data values, but the keyword here is to describe. You're not actually doing the process, so you don't need to show any specific values, for example actually calculating what you're going to describe. It's a bit like saying, well, this is completely irrelevant, find the mean of x and y, and then you need to plot them. Now, instead of me actually saying, let's do x plus y divided by 2, we're just going to say find the mean of x and y. We don't really need to do much more than actually just say what you see, and that's what describe means. So before we actually do the question, I'm just going to show you or give a brief explanation of what the actual process is. So the whole point of time series and looking at seasonal variation is that we plot moving averages, and the whole point of moving averages is it tries to smooth fluctuations that is shown by seasonal variation. As we've seen here, we have peaks and troughs because of seasonal variation, for example our ice cream example. So the idea is that we plot the average of these 4 points here that I've circled, and then these 4 points here, and so on, and keep on going up one more as we keep doing our 4-point averages. And what you should find is if you plot it in the midpoint, you get something that looks a bit like this. You get something a bit like this. I just need to know what's the actual scale, so no idea if this is actually right, but the whole point is I'm trying to illustrate, and you get something, and then you want to draw it with a line of best fit, or a trend line, what it's actually called. Now I probably should move that up a bit, like so. And basically, you're going to use this trend line, and you're going to see how much the deviation is from the actual values. And now you know a line of best fit tends to estimate values, and the same as here. You have your trend line, and then you have your values, and you have the distance between these values. You want to find the average distance between the values. And now if you find the average distance between the values and you extend this line, so let's keep extending it to perhaps something like so, like this. And now we've got our average. We can basically add on the average, whether it's positive or negative, to here, and we can do it at quarter one. And you can say that the average for quarter one, and because we're doing quarter one, we'd actually want to just find the averages for quarter one. So, and the idea is once you do that, you add the value to the trend line, and then you get your point either here, or if it's negative, perhaps here. And then that's basically your value for the estimate for quarter one of 2014, which is what it was asking for. So now we need to actually portray this into words. Well, the first thing I said is that we need to plot 4-point moving averages. And now with the average, or with the averages, we plotted all these points, and then we drew the trend line. Now the idea of where I extrapolated the data, or I extrapolated the trend line to get to quarter one of 2014, and then the mean seasonal effect that we calculated, or whether it was this value here or this value here, we added to the trend line, and that's basically the rest of the 2 marks. And each of those bullet points there is 1 mark each, and that satisfies our 5-mark requirement. The key pitfall here for most students is to describe that keyword. Most people would see, or they would think, to use otherwise, and they might actually go off on a tangent and start actually trying to do something with this graph. Now obviously I made all this data up, and I just drew this trend line completely off the top of my head, so there's no relevance to that. It was just to explain the actual process, to show you the methodology behind the actual process. And describe is actually quite a nice question, because you just have to say what you do. Just imagine you were speaking to someone and they asked you, well, how do you do this? And then you just speak to them like a friend and just explain what you're going to actually do. You plot the averages, draw a trend line, calculate the mean for the quarter one, extend the trend line, and then add or subtract to get to your actual value. The incomplete table gives some information about the number of births in the USA, the total population of the USA, and the crude birth rate for the USA in 1960 and 2021. So we need to find the number of births, and we also need to find the crude birth rate for the respective years. Now they're given us the formula. Ironically, I think this is probably the least useful formula they've given to us, and it does come up sometimes, but I just feel like they could have given any other formula, and this is an easy one to remember in some respects. But let's not moan about that, and let's just get started on 1960. This is just a simple plug and go. We know that we need to do 23.7 is equal to the number of births multiplied by 1000 divided by the total population. Now you can go with 179.3, or you can convert it into the actual number, which I'm going to do now. The mark scheme accepts both, however I'm going with the latter because technically it just makes sense to do it per person rather than in millions, but it's just personal preference at that point. Now you can do some rearranging. We can multiply by 179.3 million and then divide it by 1000. I'm just going to do that straight into the calculator, and we get the number of births is equal to 4,249,410. Now you can see why it gets a bit harder when you use this 179.3, because you'd have to do 4.249410 million. You'd have to do rounding, and it's not really good to do rounding for such a large number like that. But I'm not against that. You can do that if you wanted to do that, and it might be easier to spot that. For 2021, we don't know the crude birth rate, so we're trying to actually find it. We just plug the numbers in. We do the number of births times the total, times 1000 divided by the total population. If you type this into the calculator, you get this value. And we'll round it to 3 significant figures. The table gives information about the crude birth rate for France and for Germany in 2021. As you can see, France had a crude birth rate of 10.9 compared to Germany's 9.6. Jan concludes that the population of France increased more than the population of Germany in 2021. Explain why Jan may not be correct. The first thing is that this is a rate. This isn't a definitive number. So, well, France has a higher rate. Germany could have a bigger country. Therefore, just because France has a higher rate doesn't necessarily mean that they had a higher number. And we're not given this number, so we can't say for sure that she's wrong, but we can't say she's right either, because she could be plainly wrong. So that would be a good reason to put. Another reason you could put is the death rate. Now, it's just saying that the population of France increased, not the number of births increased. Now, the number of births, then you'd be limited to this one. You don't know the actual number of births, you only know the rate. However, since it's saying the population in general, frankly speaking, people die or are given birth to, and hence we don't know the death rate, so more people could be dying in France compared to Germany. Then we can conclude that the population might not increase in France as much as Germany. So you could also put the death rate about that. Question 13. A biased coin is twice as likely to land on heads than tails. An experiment involves flipping 9 identical biased coins. X represents the number of heads obtained in the experiment. Michael says that the values of X can be modeled by the distribution B, N, and 2/3. Write down the name of this distribution model. This is binomial. I can't really explain it much further than that, but when you see a B, that's basically B for binomial. And there's so many different distributions out there, but for GCSE statistics, you only need to know about the binomial and the normal distribution. Part B. Using Michael's model, show why the mean of X is 6. If X is the number of heads, then we can model it binomially, and where N is the number of trials and P is the probability of gaining a head. And this is literally how you write it out, and you see this commonly written in A-level. The mean of X is basically the mean of the binomial model, and the mean of the binomial model is NP. So if we show this, we can just do 9, which is the number of trials, multiplied by 2 over 3, and you get 6. And guess what? That matches the mean of x. The experiment is carried out 15 times, and the number of heads obtained in each experiment is recorded. Michael uses his model to find an estimate for the number of experiments in which the number of heads recorded is exactly 6. Find Michael's estimate. Okay, so the specification states that for these types of questions, and I'll concede it right here, binomial distribution is probably one of the hardest topics of GCSE statistics. This is the one that is set right at the back of the paper most of the time, and is set aside for those students who want to be aiming for a grade 8 or 9. However, we've kind of drawn the short straw here. According to the specification, when we have to do types of questions like this, I'll explain in a minute, but we do something called Pascal's triangle or choose notation. However, the latter is more commonly done at A level. Now, for the Pascal's triangle, they said that n will never be greater than 10, which is a nice thing, and they never typically go above 6 or 7. However, this question kind of means we have to do the long-winded way, and it makes the choose notation look much more rewarding. Now you can see why I was regretting doing this method. However, this is the method that is typically taught at GCSE, and the choose notation method is not vastly taught at GCSE, and for a reason, because most of the time it makes more sense to do it up till probably about here, and after that we get to the ridiculous coefficients, and this is Pascal's triangle. Now the idea you should have gathered by now is that you add each of them diagonally. So 1 plus 1 gives 2, and here 2 plus 1 gives 3, and let's pick a random one here. Let's say 4 plus 6 gives 10. And you keep doing that, and you basically can go on forever. Now there is a much more nicer way, and it's called choose notation, and it involves factorials and all that whatnot. However, at GCSE you're not really expected to use that method. However, here it makes sense that you would in an A-level exam anyways. But we're going to do it this way, and for 4 marks, you really wouldn't want to be doing this. That's what I meant by drawing the short straw. So the way to approach this question, so he carried out the experiment 15 times, and he needs to find a model, or he needs to find an estimate for the number of heads where it's exactly 6. Now the probability of getting a heads is equal to 2/3, and we need to label this as a success. And Q, let's say, is the probability of failure, or not getting heads, and that would be 1/3. And this triangle on the right here is called Pascal's triangle. Now I'm going to try my best to explain it as quickly as possible. We have p plus q to the power of n. This is binomial expansion. I recommend you watch a video on binomial expansion because you're going to need it here. This is when n is equal to 0. This is when n equals 1, 2, 3, and so on. And now we're looking for p plus q to the power of n, and what the idea is that when you expand it, these are the coefficients. And I'm not going to explain the actual method here because it'll make more sense in a separate video. The idea is that we need to find the value of n, which is going to be 9. And we know it's 9 because he does it 9 times here. So we're looking for that, for p, which is 2/3 plus that. So p plus q to the power of n, which is 9 because he does it 9 times. And we need to basically expand that. Now that is quite daunting, and I'll admit that is quite daunting for me. Luckily, we found it when n equals 9, we know our coefficients. I'm just going to expand it out for you. If you do not know this, don't even attempt it right now. Go and revise that question. I'm just going to expand it from now. We're interested in this one, the number where p to the 6 is equal to exactly 6 heads. And now we just need to put the value of that in. You can have 84 multiplied by 2/3 to the power of 6 multiplied by 1/3 to the power of 3, which is equal to 1792 divided by 6561, or 0.273. He does this 15 times, And since each has a probability of 0.27, it happens roughly 4 times. Part D. Write down 2 assumptions which Michael needs to make about the experiment so that the distribution of the binomial model is an appropriate one to use. I'm going to quickly write BINS. It stands for binary, independent, number of fixed trials, and same probability. The idea is they are your 4 assumptions, and now you only need to choose 2 of these, so choose any 2 from these 4 letters. And the main thing that you need to do is need to put it into context. I'll go with the 2 simplest ones, that the probability of heads remains constant at 2/3, and that there are only 2 possibilities. You either get a heads or not a heads, i.e. tails. I'll concede that not only is this a difficult question to be doing in the exam, but it's definitely difficult when it's 10 o'clock at night and it's quite boiling today. It's quite a hot day in the UK for once. Anyways, this was paper 2 of the specimen hire.